In my previous video I have run a simulation of different types of airfoils and have compared the results with the wind tunnel data. And the correspondence was pretty amazing. So for instance, here we have the red lines, the measurements from the wind tunnel, and the blue line is a simulation of XFOIL. And I have run this simulation and comparison for different types of airfoils, and the results were surprisingly good. So almost identical results for the simulation and for the wind tunnel data. It's quite surprising. So after that, I was ready for the next step. And the next step is to choose the best possible airfoil for my application. So at this moment I have the wind tunnel data for many different types of airfoils. I have huge collection of wind profiles. I have the XFOIL software, which allows me to receive results very similar to what I might have from the wind tunnel data, and so on. So I have all those beautiful tools, all the collection of data and airfoils and so on. So the next step is to compare those airfoils. To compare those airfoils, we have to know how to compare them. For instance, we have to know the lift coefficient, because the lift coefficient may vary, but it's depends on the speed and the mass of the plane. For instance, if you go fast and you have certain weight of the plane, you don't need to have huge lift coefficient. You might need just 0 point something, 0.0, maybe 1. Depends on the speed of the plane. So all those parameters are known. So the only question remains how to find the lift coefficient. The lift coefficient needed for the optimal operational point of the plane. And once we know this lift coefficient, we can look at the drag for different types of airfoils and choose the airfoil with the minimum drag, and so on. But first, let's find the lift coefficient. Initially I was thinking this is a trivial task. If you know the lift coefficient for a two-dimensional airfoil, just multiply by the length of the wing and then you have the total lift. But it's not true, actually. It's a bit more complex. So what, for instance, you can do, you can look into the lifting line theory. So what this theory says, that if you have a wing, let's say this is a wing, and then you might divide this wing into the sections and compute, for example, lift force for each section, and then a simple person would think you just sum them up and you get the total lift. But this is not true, because each section affects the section, the neighboring sections. As we know, for instance, when you look at the calculation of the lifting force, we look at the circulation around the airfoil. The same kind of technique is used for this lifting line theory. So we look at circulation not only at cross section of the wing, but also circulation along the wing itself. And so the few theorems are involved in this process, and it's actually becomes a bit ugly very fast. The few equations are available. For instance, the equation for the lift coefficient, which is determined by the aspect ratio of the wing and the angle of attack, and so on. So the few simple equations are available, but in the essence it's not that simple. You have to do your work and get the right results. But before doing this, the idea was to find some sort of software which is going to allow me to compute the lift coefficient for the wing, for the three-dimensional wing. And I found it. So here is the software. This software consists from two parts. The first part is actually the same as XFOIL. It uses the same source code but written in C, not in Fortran. Works significantly faster, and as I found from experiments, it's more stable, does not go into the infinite loops. And the second part is the Win design part. So from there we can find the lift coefficient that we need for our application. But first let's take a look what the software can do for us. Maybe we can find some new features and so on. So here is our beautiful software, and the first step is to load an airfoil. So we open a file. So this file is a regular file, as we have seen previously, with XY points, and then we have this airfoil loaded. So the first thing you would probably have to do is to play with style. So I would like to have it red. I would also like to see the points. Okay, those are the points, and we know that in this particular case we don't have too many of them. So what we should do, we should go to the design, refine globally, the option. At this moment we have 28 points. So let's put a bigger number, at least 100. Okay, now we have more points, and then press OK. Okay, so I'll write the old one. So we have this beautiful airfoil at this moment. So this is the first step, and the second step is to run the simulation. So to run the simulation, we go to the analysis, define analysis, and then just the simplest case, the most easy way to do it, just to use automatic. Then the name of this particular analysis, so this default name, you can put something else, and we can know that this name actually contains the parameters of the simulation, for instance a Reynolds number, the Mach number, and the critical number. So those numbers can be set here. So Reynolds number is 100,000. So the critical number, the Mach number is 0, and the critical number is 9. So this is important option. So those two are important for the slow flying airplanes. And as we have seen from the previous video, to feed the data from the wind tunnel, you might need to increase this number to 11, maybe higher. So this has to be kept in mind, that this number might be modified. And once again, so those numbers are actually inside of the name of the file which is created for this simulation. So we press OK, and now this window. So this is the simulation window. So what we can do, we can choose the starting point, say minus 5 degrees to 13 degrees, and here's the step. I'll put a bit bigger step, 0.5 degrees, and then what you do, you press analyze. Oh yes, and you also make sure that you have the points checked here. So viscous solution, initial boundary value. So basically it's going to reset the boundary, layer, initial conditions, and the store option. So anyway, so you just press analyze, and now we see it's running, and then the results is ready. So it's very fast. So the result is obtained incredibly fast if you compare it with the XFOIL, the original software. So this solution is definitely faster. So now what we can do, we can look at the actually what we have, what we can see right away, all the results we have obtained. So if you pressed show all ops, you get those results. So those are calculated values, and you can see that we have many of those things, and it's a bit confusing. So what we can do, we can just press show current op only. So we have this single graph, and this graph depends on the position, the angle of attack So in our case we use angle of attack, we use sequence, so this is the angle of attack. You can put any value, let's say minus 3 degrees. So we have kind of graph we have seen previously in our simulation in XFOIL. And what we can do now, we can use a very beautiful thing. If you use this window, you just use mouse to click it, and then you use up and down arrows. You can see how it's going to change the angle of attack and going to show the different graph corresponding to this angle of attack. So let's go. So now the airfoil is lifting up, and also the different graph is shown. Okay, this is fun. Let's make it more useful. So what we do, we use this section and show boundary layer. We can also show the pressure. So the green arrows showing the pressure. So if we once again click the angle of attack and move it up, increase it, we see how the pressure is changing, and we also see the separation happening. So to make it more distinct, I will change my color from red to say blue. Okay, now airfoil is blue, and the boundary layer is shown in red. We can scale it down using the wheel of the mouse. Okay, so let's continue to go up. So you can note that at this moment we have a very peculiar effect. So this is the separation of airfoil happens at this position. You can zoom in. We know that here is the separation happening. So this is the blue, the airfoil, and the red is the boundary layer. And at this point we have the separation. So here is the almost at the very tip of the airfoil, the separation happening. And then it's going back to the airfoil, so kind of retouching here. So let's look once again. And boom. So here's the turbulent region between the boundary layer and between the airfoil. So the air goes like that. We have the turbulence happening. And then if we zoom out, so the XFOIL, so this software is basically XFOIL simply written in C. So the simulation area is finite, and it does not converge back to the laminar flow. So we have the turbulence in the back. That's actually happens exactly that in reality. So once again, so we have the separation happening, and we see that these things continue to be turbulent. And above the boundary layer we have the laminar flow. So if we go up, it becomes even worse. So right away we can say that this airfoil probably has to be used only in the ranges of angle of attack. The angle of attack should not exceed this value, which is 8 degrees. If you exceed this value, you would have separation of the airflow from the airfoil. Okay, so this is fun. You can play with this basically interactive way and see all the features of the airfoil. But what's about the polar graphs? So you press this button and boom, you have it all the same on this figure. So once again, if you compare those graphs with the XFOIL, it's definitely more explicit and clear. It shows more information, and it's kind of so those graphs are better, and let's use a very interesting feature on this plot. So if you go to the graph, and if we use highlight current operation point, we know that we have this square, which actually shows at which position we are. So once again, this is the operational window, 9.5 degrees of alpha, and this point is here. And once again, this is very nice, cool feature. Once again, let's play with the with this window once again. So we choose the minimum value, -4 degrees, as we have done it here. So -4 degrees, the angle of attack is negative, and the polar point is here. So what we do next, we just press this window, and then we go up and press the arrow key. Boom, boom. Yes. So you can also change the style and change the style of this graph. It's can be done here. So I would like to see the actual data. So this is the points which were computed. So once again, let's go up, and we go from point to point, increasing angle of attack. So at this point we have -1 degree, 0.5 degrees, 0 degrees. So this is the 0 degree point. And you also know that the point moves at all the graphs at the same time. It's very convenient, so you know exactly where you are and how those graphs are connected. Go back. So it's very cool. It's a very cool feature. Okay, so this one thing, and the second thing is that, for instance, you might wish to add some points like in this range. So you know that, for instance, here at 8 degrees to 9.5 degrees, the points are missing. So maybe you would like to have more points. So what you do, you go here and change the range. So you choose from 8 degrees to, let's say, to 11 degrees, and then you increase the resolution. So say 0.1 degrees, press analyze, and note how the points are appearing on this graph. So here's the range. So the new points, not present previously, are appearing on that graph. The same is here. You can zoom in with the mouse wheel and look at the new points. So just showing this just for arbitrary range, but in reality this might be very useful when you have some strange behavior. For instance, the graphs behave not in the physical way. You have some points which are not supposed to be there. So if you do this for this particular range and you use a finer resolution, you might be able to fix this issue. Okay, so this is the polar, and this is the usual plot, the pressure plot. So this is the upper pressure. This is the pressure at the lower surface. The upper surface and the lower surface. Okay. And I have plotted this figure just to be more explicit. So once again we have this airfoil, we have the separation of the flow, we have the turbulent region, so we have the boundary layer, defined by the red line and the turbulent region behind this line, and laminar flow above this line. And we also know that because of this huge boundary layer, well, in the simplest terms, basically we have the effective profile of this airfoil different following the boundary layer, and so the drag is high as well. So this one remark. So second remark is a remark on the simulation. Analysis, when we press the analysis, we have this option XFOIL advanced settings. So these settings allow us to change the number of iteration. By default we have 100, but if we are going to load some strange airfoil with turbulent flow, we might need to increase this number to 200 or maybe even 1000. At least in XFOIL it helps. So this one thing, and the second thing is time between the graphs updated, so you can place this time as well. The use of XFOIL was actually a bit challenging because sometimes the software was kind of going into the infinite loop, and there is no way to stop this process except you have to exit with this software. So in this case, like, I haven't seen it crashed even once. I haven't seen it go into the infinite loop, so I think it's more stable in the sense. So you don't have to start this software once again and to define all the parameters once again and so on. But in XFOIL I had this problem, and I was having a bad thoughts about the idea to use Python to control it and for the mass batch processing of different airfoils. So, but in this case it's all good. So this one remark, and the second remark is that you can save actually those the data you have computed by pressing this Polars menu and choosing the export option. And then you just name your file. Let's say name it 1. No, I'll keep the actual name because the name includes the Reynolds number and the critical number and so on. So I just put this one in front, press save, and then we can look at this file. So here is the file, and here is the content of this file. And I was pleasantly surprised by the result, because this is exactly what you have in XFOIL. And for me it's very important because I have written Python script, so I can plot this graph independently in Python right away. So I don't have to do anything else, I just use this file to plot my graphs. It's very good. What else can we do? Very cool feature is in the software batch analysis. So go to analysis, we can choose this option, batch analysis or multi-threaded batch analysis, depending on the system you have. You might use many threads to analyze. It's going to be faster, I think. So let's use this option. Here is our window. What we can do now, we can, for instance, change the Reynolds number range. Plot those graphs for different Reynolds number. So I can set a range, or I can choose a list. So here's the list, place this list, or I can set the range. So I'm a bit lazy, so I use a range. So let's say from 50,000 to 400, and I use increment to make it fast. Is it 100? Again, the critical number, the transition where it might happen, so we can force transition at early stage. For instance, if you are using turbulators on your wing, then you might put those numbers closer to the tip, but we just let it go, and so it happens. So there is nothing which causes turbulence, so it's going to happen by default by 1. Okay, so the alpha goes from -5 to say 12 degrees. The step is 0.5 to make it fast. Okay, so let's run the analysis. Here is the log. Okay, analysis complete. Close. And here's the graphs. So what else can we do? We can look at each particular graph separately. So for instance, going here, choose graph number 1. Here's the graph. So this airfoil, the lift coefficient versus drag coefficient is computed at different Reynolds number, and the step between those Reynolds number is 100 thousandths. And we know that those graphs are a bit different and probably not very physical at some point. So what we can do, we can increase the number of points and play with the particular ranges of this simulation and so on. But the idea is it's very simple, that you can calculate many different parameters or many different graphs using this batch processing technique. And also what you can do, you can save all the results. So what as we have done just a moment before, we just choose export. Once again, polars. Let's create a new folder. Okay, so I think it saves the current folder, the current polar at given range, but let's save all of them. So here is the option. So you press polar menu and then you press export all polars, and then you select the folder. In our case, folder is 2, and then it's done. If you look at those files, we see that this folder is populated with plenty of different files. Each file was taken a different Reynolds number, so 50, 100, 150, 250, 350. So we have those thousands. So we have those different Reynolds numbers and we have different results. If you go inside, you know the Reynolds number is a bit different, not a bit, but different Reynolds number, but the same parameters are the same. Again, so Reynolds number is different, and so on. So we have saved all the data for all the Reynolds number, and we have done it very fast. Okay, I think I should stop at this moment, and maybe we'll continue in the next video. But for now, I would like just to jump to conclusions and say that the small problem with the lift coefficient have led me to the discovery of this beautiful software. So this software consists from 2 parts. In this video we have reviewed the first part, and this part is similar to XFOIL. Basically it uses the same source code as XFOIL, but written in C, not in Fortran. This software runs faster, significantly faster, and is more stable, does not go into the infinite loops like XFOIL does sometimes. It's also more user-friendly and interactive. You can play with an airfoil, change angle of attack, observe how the boundary relay is changing, and so on. So it's very convenient and user-friendly. You simply can analyze airfoil right away and compare them with the other airfoils. So this is good. The software also has the batch processing feature, so you can simulate the behavior of airfoil for different valence number or how the different airfoils behave. You can simulate few airfoils at the same time and so on. So it's very convenient, and there is no need to write a script in Python to control the XFOIL.